So, hello and welcome. This is the How To Talks by Postdocs, and today we have Dr. Koebley, who's going to be talking to us about Bayesian statistics. Dr. Koebley is an Aracta Research Fellow in Jason Reed's lab in the physics department here at VCU. He is researching a novel method for detecting genetic mutations using biophysics. Formerly, he taught middle school mathematics in Boston and DC before earning his Ph.D. in applied science from the College of William and Mary. Let's welcome Dr. Koebley, and here we go.
Hi, everybody, and thanks, Stacy. I'm very excited to be here today and share with you kind of this adventure that I recently went on with some of my research to dig into Bayesian statistics. Maybe today I want to propose an alternative to the beloved or perhaps hated p-value and see what you all think. So let's buckle up. So let me get my screen shared here, and we can do this. All right. Are we good? Can we see that? Great. Okay. Maybe you've just heard of Bayesian statistics. Maybe you have some familiarity with it, or maybe you think that Bayes is the plural of a significant other. Either way, this talk is for you. And I really do hope that it transforms the way that you think about setting up and interpreting results from your experiments. What we're here to do today can be divided into 4 aims, but before we get started, I want to lay out some norms for this talk. I want to say that you can feel free to interrupt if you've got kind of a pressing question or some clarity at a point. You can also enter questions in the chat. I probably won't see those until the end of the presentation, but there will be some time hopefully to answer some questions. This presentation is going to be recorded. I've got some extra materials for you as well. So any code you see, you'll be able to pick through and dig through on your own. I tried to make it as step-by-step as possible. I really do want it to be something that you can take and use on your own. I do want to give a warning that there will be some math and some math symbols, just a little bit, maybe just a little bit of algebra. But I don't want you to get too overwhelmed. We're going to do it together. And I just want to let you know that if you get lost or you don't get 100% of this, don't just check out or feel like this is not for you, because it took me a few times to get this. And we're really just going for broad strokes today, introducing some vocab and letting you kind of see what this process can do. So any questions before we get started? Okay. So our aims today are, first, we're going to describe some limitations of frequentist statistics or the p-value and null hypothesis significance testing. And then we're going to derive Bayes' theorem and intuitively describe its terms. We're going to use Bayesian inference to determine if 2 normally distributed groups have credibly different means. This is kind of the classic, or one of the classic uses of the p-value. I want to see how Bayesian inference can do with that. And throughout the talk, we're going to be referencing useful resources for practicing frequentist and Bayesian inference. So first, we're going to start with describing some limitations of frequentist statistics. And here's a comic from XKCD. Maybe you've seen it before. It's one of my favorites. But you've got some aspiring researcher, perhaps, or someone who's got this pressing question, thinking that jelly beans cause acne. And the scientists check it out and find no link. But the person with the question says that they think it's only one color. So the scientists try a bunch of different colors. In fact, they try 20 different colors of jelly beans. And in one of those cases, the green jelly beans, what do you know? They find a significant result. And so this is this crazy, incredible result that green jelly beans are linked to acne. And of course, this is kind of ridiculous, and it's set up with, or this is a result of the way that we interpret or misinterpret the p-value. So just want you to take some time right now. By the way, if you don't have a piece of paper or a pen, I think it's going to be very useful during this talk to have at least 1 or 2 pieces of paper so you can follow along with some of this stuff. But I want you to take maybe 30 seconds right now and write down what you think what the definition of the p-value is. See if you can do it. without Google, see if you can just do it off the top of your head. And no worries if you don't get it 100% right. I'll just give you about 10 more seconds. Okay, do we have any brave volunteers? Someone want to give this a shot?
Yeah, I'll try. So I wrote P-value is the statistical value that is used in relation to an alpha value in order to reject or accept an hypothesis.
Okay, yeah. So you're, using it as a statistical value to reject, or did you say reject or accept the null hypothesis?
Yes.
Okay, yeah. It's close. It's kind of hitting around the borders. I think you've got some of the main ideas. I will say one issue with that is that actually the p-value is not telling you whether or not you can, or it's not a value of whether you can accept the null hypothesis. It's only telling you whether you can reject the null hypothesis. So yeah, but
thank you.
No worries. Yeah, there's well, we'll see. It's not easy to get this whole definition right. Anybody else want to?
I have one that I'm willing to volunteer.
Sure.
P-value are the odds that in a normally distributed population, the difference that you see between the groups occurred by chance.
I'm glad you said that, and that's one of the main kind of misinterpretations that we might have of the p-value. It's not actually giving a probability that two things would happen by chance. I know that's kind of what it seems like, what it should be. It's not really what it's saying, but I mean, again, you're not alone. That's what a lot of people, and that's what I think, a lot of us believe what this is, because that is the most intuitive interpretation of what, the results are when we do a statistical test. Anybody else want to give one more?
Want
to give it a try?
Can I try?
Sure.
Sure. I have, so it's the probability, given that the null hypothesis is true, that you will observe a value equal to or greater than the value observed.
That's it. That's the one. Yeah. So it's a very specific definition. That's what I think, I want to get across here is the p-value is the probability of obtaining an observed result or more extreme results, depending on how you conducted the test, given that the null hypothesis is true. So in math language, or math terms, this is how we would write this. We'd say that it's the p of the probability of everything that's in the parentheses. Your result, or x, is greater than or equal to the data that you observed. So what the x, so that's the probability of getting some result x that's greater and equal to than the data that you observed, something more extreme than the data you observed. Given that, that's what that straight line is. It means given that, the null hypothesis is true. So again, very specific and maybe a little unintuitive, not really what you're thinking when you get some results from a statistical test. And just want to put it out to you, maybe to see if anybody has some thoughts here. What do you think? Is there another probability that would be more aligned with the goals of an experiment? Is there some other way that we could, something else that we could try to get from our experiment that would be more aligned with what we're trying to actually discover? It's okay. I mean, and maybe what I'm looking for is something similar to what the first two volunteers said, which is, again, a more intuitive understanding of what we're looking for when we do an experiment.
What about, what about the probability that the hypothesis is true given the data?
Right, exactly. that's kind of, to me at least, and maybe, maybe to some of you, that's what I'm looking for when I do an experiment. I'm trying to find the probability that the hypothesis is true, given the data, right? It's kind of a switch of what we're seeing written down right here. You're trying to find the probability that whatever parameters you're looking at happen to be true, given that you're seeing the data that you observed. And we'll get back to that later, but that's actually exactly what you're finding with Bayesian statistics. So just keep that in mind as we go through this. I just want to lay out real quickly some of the other issues that you can see with null hypothesis significance testing and the p-value. The one that we just kind of, I think, explored there is that it can be confusing, unintuitive, and also I'm going to throw in there dependent on assumptions. I know any of us who've done a null hypothesis significance test know that you have to, in a lot of the classic tests, you have to assume normality in your data, which, there's additional tests you can do to try to see if that's true with your data, to see if they're actually normally distributed. But if they're not normally distributed, then you have to do a bunch of other stuff. So it's just, it's complicated, and perhaps needlessly complicated, given that there might be some other options out there. This is one that I think a lot of us are aware of as well. The p-value is dependent on sample size. So this can give rise to what's known as p-hacking, where you take a bunch of samples, you don't get the result you want, perhaps. This is some nefarious researcher doing this. I know none of us would ever do this, but you don't get the result you want, and then you do twice as many experiments, and then suddenly your p-value is below 0.05, and so then you stop. So that's kind of these, and because it's just a single value, there's no other kind of interpretation or additional context for a p-value. It can be difficult to see where that n comes in, or what the reference is for that. So here's just a quick example of this from this paper from 2011. If you're trying to test the effect of a drug, atropine, on a control, what we're going to see here is just mapping that effect as we take more and more samples. So if you just take 10 samples, the difference between the means looks negligible. They look very similar. And so what I'm plotting here is on the top, the p-value. If you do a p-value between comparison between these two groups, and you can see that magic number of 0.05 is anything below the orange. So all those tests that you see when your sample size is very low are mostly above the orange. So as you get through past. But then as you get to more and more samples, you see your p-value dip below that orange line, which means you're getting significant results all of a sudden once you get over 1,000 samples. Now below, the plot below, you can see the hedge is a G, or one way of calculating the confidence interval. And it looks a little different and maybe more useful. You can see it's starting out very wide, meaning that there's a lot of uncertainty as to what the actual effect of the drug is. And then as you get more and more samples, you can see that confidence interval narrowing. So it's above zero. So you're seeing that significant result, which means you're seeing some effect that you can assume with confidence is more than zero. But it gives you more context, basically. And that's one of the lessons maybe that I'm sure many of us know, but I want to reinforce here is that the confidence interval is better than the p-value. Gives you more context, still has some issues though. Another kind of weakness of the p-value is that it's one outcome based on the possible results from other outcomes, the intention. So there's this whole cloud of possible outcomes that is implicit when you read a p-value. It's not really based on the observed data, which is a bit of a complicated concept. But I think the one that kind of drives it home for me is an ANOVA test. If you get a situation like this, where you get a p-value of 0.05, less than 0.05, well, it doesn't really make sense to base your p-value just on that single test, because your testing intentions included the sphere of all those possibilities, all those different colors that you were testing. So in ANOVA, you have to be very careful about this. You have to adjust you have to apply some normalization factors and really be careful about how you interpret those results because of this exact effect. One way to kind of enhance your null hypothesis significance testing is to use a confidence interval instead of or in addition to a p-value. Definitely a good idea. I'll give you a resource if you're not aware of it in just a second. That's my favorite for kind of dealing with null hypothesis significance testing. But I'll say that the confidence interval still suffers from a dependence on intention, and it's just 2 endpoints. It's not actually giving you a distribution of where the most likely values for a mean, say, might be. So when you see a confidence interval, you're just seeing 2 endpoints. Also, not as great as you might want. And this is one of the main kind of weaknesses of null hypothesis significance testing that I think is kind of shocking in some ways if you look at certain examples. So, for instance, if I'm looking at a fair coin, I'm trying to see if a coin is fair, and I run a bunch of experiments to determine that by flipping a coin. What will my null hypothesis be in this case? Anybody want to volunteer? What's my null hypothesis if you're trying to test to see if a coin is fair?
That the coin's not fair?
Well, I think, that's, actually, I'm looking for like maybe sorry, maybe I was unclear about this. I'm looking for maybe like a number. So what percentage of your flips did you expect to be heads? So sorry, so maybe that would be a null hypothesis. Is there a way that you could use that? So if I'm saying if I'm looking at the number of
zero difference, 50-50.
Yeah, 50-50. Sorry. So yes, so your null hypothesis in this case would be that the chance of getting heads is 50% or 0.5. Now, what if we're testing a nail? We're seeing what's the chances of getting heads when you flip a nail, where heads means the nail lands directly on the head of the nail. So if we're asking if the nail is fair, we actually have to use the same null hypothesis. This is the crazy thing about testing null hypothesis significance testing. You have to, if you're trying to disprove your null hypothesis, you have to, use that null hypothesis. So it's actually the same null hypothesis that the chances are 50-50 that you're going to land on heads. And again, this is maybe a weakness that you might have seen in some of the literature, people testing null hypotheses that have no chance of being true. So they might test, you might say, all right, this drug has no effect. Well, we can be pretty sure that if it's a drug that's an iteration of a previous drug, it has some kind of effect. So that's what I mean. It can be really, really difficult, or doesn't make a lot of sense to assume a null hypothesis that a nail is fair or that a drug has no effect when, it's pretty clear that the nail is not fair or that there isn't some effect. So the way I want to put this in terms of this saying that there's no prior knowledge that we have. There's no prior knowledge built into a null hypothesis significance testing. And in Bayesian statistics, there is prior knowledge that you can build in to your tests. So just kind of as a summary here, there's a lot of issues with the p-value, but it's not going anywhere, I don't think, anytime soon. It's still widespread in academia, especially. And, I think we should definitely learn how to use it as best we can. This is a great resource if you don't know it. Even if you don't work in biostatistics or biology at all, this is an amazing, intuitive look, very little math, a lot of intuitive explanations. So I highly recommend it. Moving on to our next aim. We're going to derive now Bayes' theorem and intuitively describe its terms. So we're going to get started with what Bayesian statistics is and how we can use it. So just a brief background. Bayesian inference has actually been around before null hypothesis significance testing. It came about in the 1700s. Thomas Bayes was an English mathematician. So it's been around before null hypothesis significance testing, but it wasn't as widely used for one major reason that we're going to get to in a second. It had one major flaw that made this other technique of the p-value come to preeminence. So Bayesian inference, as simply as I can state it, is the reallocation of credibility towards parameter values theta that are consistent with the data D. Okay, so that may seem like a mouthful. We're going to break this down. Okay, when we say a reallocation of credibility, you're starting with your prior knowledge. Okay, and what's great about Bayesian statistics is you can be extremely explicit with how you define your prior knowledge, what exactly you expect your parameters to be. Okay, so when we talk about a prior knowledge in Bayesian statistics, we're actually talking about this value here, the probability of theta, or the probability of your parameters being true, a certain set of parameters being true. So this is an initial, a naive, or it can be informed by prior data as well. So you might have some preliminary results that give you some idea of what theta should be, and this is your prior knowledge. Then you refine or you reallocate your guess or your knowledge based on the data D to get your posterior probability, or the probability of your parameter values theta being true, given that you've collected the data that you've collected. So again, this is a much more intuitive desired endpoint of experimental inference versus the p-value, where those values are essentially switched, where you're looking at the probability of some result greater than your data given the parameters. Here, you're actually finding the probability of your parameters given the data. So you collect the data and you say, all right, how does that affect my understanding of what the parameters should be? So let's do this. All right, everybody get out your paper and your pencil, and we're gonna derive this together. And I think it's only fitting that we start with an example that might be on the minds of many, which is March Madness. We're gonna do a March Madness example, and we're gonna do March Madness winners since 1979 is what we're going to work with here. Let's see if I can get black instead of red. So I apologize if my writing isn't the best here. I'm going to do my best. This is my wife's touch screen, and it's going to be great. It's going to be great. Okay, so we're going to make a little table here, 3x2 table. And our columns are going to be the seed of each winner. So if you're not familiar with basketball or March Madness, the seed is like the ranking. And there's actually 4 number 1 seeds every year, because each division or region or whatever gets their own number 1 seed. So we're going to divide this into 2 columns, whether you're a 1 seed or a greater than 1 seed. Do that, leave a little bit of space at the bottom there, and that's what we got. Okay, and then our rows are going to be our teams. Okay, we're going to do the 2 programs that have won the most championships since 1979, UNC and Duke, 5 each, and then we're going to do everybody else. So, and we're making this table because Bayesian statistics is dependent on conditional probability. This is a really nice, simple way of looking at conditional probability. And yeah, don't get too hung up on what these particular values are. I want you to think about the logic that we're trying to build. And for that purpose, we're going to call these seeds or seed options our parameters. Okay, call those our parameters theta, and we're going to call our teams our data D. Why did I choose the seed to be the parameters? No reason. Could have been unswitched. I just want to start to get you used to thinking of the relationship between data and parameters. So we're going to call this number 1 seed theta 1. We're going to call this greater than 1 seed theta 2. UNC is going to be D1, Duke is going to be D2, and then other is going to be D3. Okay, so let's fill in our table with some real data. There's been 40 championships since 1979, and what I'm going to give you is the probability of UNC winning as the number 1 seed. That's what we're going to put in this little square right here. The probability is 0.125 based on that last 40 years, or those 40 championships. So I think that won 5 out of 40 when they were, and every one of those times they were ranked the number 1 seed. So actually it's 0 times that they were not ranked the number 1 and also won the championship. So we're just going to fill in the rest of those values here. Oop. That should be 0.025. Got 0.35, 0.4, and that's it. So we're going to add to our table here. I'm going to start with our first kind of, well, maybe not our first, but one of the major vocab terms that you'll come across. And sorry, that's an M for marginal. So we're gonna describe our marginal data. Marginal just means unconditional. So there's no condition that's applied to this value. And how we're going to get that, we're just going to sum up all of the data in one row. So I'm going to get 0.125 by summing up 0.125. I'm going to get the same for Duke when I sum up everything in that row. And then for everybody else, we're going to get 0.75. Now I also have marginal parameter values. And so I'm just going to sum every column. 0.575. So the chances that the winner was a number 1 seed, which is kind of interesting, I thought. It's very likely that the winner of the tournament is a number 1 seed. And 0.425 is the chances that they weren't number 1 seed. So, okay. So this is our table. We've defined marginal. Now let's ask some questions. And one of them might be, what's the probability that, again, a number 1 seed won the tournament? That's this value right here, or P of theta 1. So that's what we call the marginal probability of theta 1 being true, or our prior knowledge. It's unconditional. There's no conditions on this knowledge. It's just the probability of theta 1. You know, we can also have over here probability of D2. That's the marginal data, or the probability that Duke won a tournament. So those are relatively easy. Let's go on to a tougher one. Let's say, what's the probability of theta 1 given D2? Or the way we would say this is, what's the probability the winner was a number 1 seed, given that we know already that Duke was the winner. Say we're only considering cases where Duke was the winner. What's the probability that the winner was a number 1 seed?
0.1.
It is not, actually. And this is here's where we've got to think about that given term. So when we say given that the winner was Duke, it means we're focusing only on this row. We're only focusing on the cases where Duke was the winner. Okay. So I think this is really important. This is kind of the whole, and you'll see in this the definition of Bayesian statistics. What we do when we say given that something is true, it's actually giving us a new focus. Or another term for that is we're reallocating our probability based on what's given to be true. So think about that one more time. Given that Duke is the winner, we're only looking at cases where Duke is the winner. We're focusing in on that row. We want to look at the cases where the winner was a #1 seed, and Duke was the winner. Does anybody have any? I thought.
0.8 then?
Yes, that's it. Yeah, and if we're not sure how we got 0.8, we're looking at the probability that the winner was a #1 seed and the winner was Duke. So that little comma means and, which is this term right here. We're dividing that by the probability that the winner was Duke. So again, we got that new focus. And hopefully this, if you, again, this maybe you're not 100% getting this, but think about it a few times, maybe come back to this and see if that makes sense. Given that Duke is the winner, it means we're in this row, we're focusing on this row. What's the chances that the winner is a #1 seed? It's this guy divided by your total or your marginal value. So seems simple, but it's actually a very powerful concept, as we'll see in a second. But I want you guys to maybe try this one more time with a different question. We're gonna flip it. Okay. Given that, let's try this instead. Given that the winner was Duke, what is the probability that the winner was a #1 seed? So I'll say it again. Given that the winner was Duke, maybe I'll write it off in this corner. I'm running out of space. Given that the winner was Duke, sorry, given that the winner was a #1 seed, what's the probability that the winner was Duke? And maybe you don't have to calculate this exactly. You might need a calculator for it. But does anybody have the problem or the division problem that you would use here? The numbers that you would plug in?
Would it be 0.1 divided by 0.575?
That's correct. Yep. Yeah, so this time our focus is the column, is that first column. So that's the reallocation, is based on that P of 0, or the probability that the winner is a #1 seed. Cool. So again, let's keep these concepts in mind, and we're going to do some derivations. Oop, there's that question that I just asked. So again, this is recorded. So if you didn't quite get all that, it'll be on there. So here's what we just wrote down: probability that the winner was a #1 seed, given the probability that the winner was Duke. Okay, that P of θ1 given D2, and that's the intuitive kind of definition of conditional probability. If we just generalize this, okay. Now we're moving away from that table and those specific examples. Let's just think about sets of parameters theta and sets of data d. Okay, so for any set of parameters theta, this still holds true. This is kind of the power of this basic logical relationship of conditional probability. So here's the algebra. Again, you may not, I might be going a little too quick now to follow along, so maybe you can just absorb this and absorb the beauty of Bayes' theorem. We're just going to switch theta and d. It's the second question that I asked. You can consider focusing on a column instead of on a row and get this relationship. P d of theta, or PD given theta, equals P of theta and d divided by P of theta. Oh, we can multiply, here's the algebra. Multiply both sides by probability of theta, and we see a common term here, that and term. So we can plug that in to your original equation, and that's Bayes' theorem. That's as simple as it is. So the probability of theta, or your parameters, given your data, equals your prior parameters, P of theta, times the special term P of d given theta divided by P of d. So this is where the vocab comes in, and I think it's pretty important. So I would write down Bayes' theorem and then write down each of the definitions of these terms, because they do pop up quite a bit, and it'll help you kind of keep your bearings. So this that probability, that P of theta given D is called the posterior. Again, that's kind of our intuitive, most intuitive endpoint of an experiment. That's our prior. There's no condition there. It's just the probability of your parameters, your naive guess. This is called the likelihood, this term, probability of D given theta. And we're going to call that red term marginal data. There's actually got a bunch of different terms, and I'm personally not a fan of any of them because they're all kind of misleading. So we're just going to call this the marginal data term. Okay. So here's Bayes' theorem, and we're going to see how this would work when we actually get some data and do an experiment. So for example, say we're considering normally distributed data, and maybe we have the parameters of a mean of 5 and a standard deviation of 2. You can see up in the right-hand corner. We know that our equation for a normal distribution, or the probability of any, or the probability distribution function for a normally distributed equation is this: the P of some term of some number X given your mean and standard deviation is as it's written there. So we can say, we can find a prior just by using our prior knowledge. So for instance, perhaps the probability of a mean of 5 and a standard deviation of 2, you think is 20%. You think that's a very high probability. Remember, we're talking about probability, it's got to all add up to 1. So this would be a very high percentage. You think maybe this is the most likely mean and standard deviation. And you could just set that. And by the way, you can set what you're actually going to do when you do this is set a distribution for your mean and your standard deviation. You're going to say, this is what I think the most likely distribution of my means are. This is what I think the most likely distribution of my standard deviation are. And then you can just use those based on your prior knowledge. Okay, then there's this likelihood term. Say that this is the data set we got, 3 points, 5.5, 5.6, 4.2. What we can do is to find the probability of this data given our parameters, PD given theta. We can just plug it in. Likelihood function is just plugging in your values. And if you think back to how we calculate the probability of independent events, what's the probability if I get 3 heads in a row when I flip a coin? You multiply the probability of each case. So that's how you find the likelihood value. You multiply the probability of each individual data point. So in this case, you can see here, I just plugged in the values of 5.5, 5.6, 4.2. Very easy for a computer to do this. And you can get a value there of 0.0068. So, so there's what I was saying about your parameters. If your parameters are a distribution, then your posterior is a distribution, which is a very interesting thing. We're not just getting a single p-value. You're going to get a distribution of your most likely means, your most likely standard deviations, instead of just a single value. And then you can use that to make your inferences. But just want to hit this home. I starred the prior and the likelihood because we can find those, given that we know what our, we have some prior knowledge of our data. We can find those 2 values. You can actually plug in numbers for those. It's that last term, that marginal data term, that's been the trick. And this is the reason actually Bayesian statistics hasn't been used in the past, is because that marginal data term, you can see how I just laid this out in a general table. You've got to include all possible data sets, which seems like an impossible task. And there's ways we can massage this term to make this possible. So that P of D term is just the sum of all those, everything in that row. But if you remember that P D of theta term, or P of D and theta, we can actually look back to that derivation slide and see that we know an equivalency for this. So that's equal to our likelihood times a prior. So actually P of D is just the sum of all of our all possible priors times the data given that those priors. So it's the prior times the likelihood for all possible priors. Still seems tough because you have to sum all possible priors in the denominator there. You have that infinity term, and I probably could have used an integral there instead of a sum term. And the question is, can we, and sorry, those i's should be subscripted. I'll fix that when we go back to this. That's the trick here. Can we find some way to test all possible sets of priors, or do we need to? And anytime we get into infinity or close to infinity, you should be thinking, all right, maybe this is a good job for a computer to try to get close to the answer in an approximation that is close enough. And in fact, that's the way to solve this. And that's why Bayesian statistics has become more possible. The integrals in the bottom of this equation were impossible basically before, except in some special cases, before, they're still impossible to analytically solve. But with computers, we can computationally solve them. We can do enough tests where we get a close enough answer to this. So that's the key. And maybe I'll go through this real quick. In order to do this with a computer, you're using something called a Markov chain Monte Carlo analysis. It's a really cool and simple technique. And I love this example. Say you want to visit an island a number of times proportional to its population. You're a politician and you want to visit every single one of your constituent islands, and every one has a different population. Problem is, you don't know how many islands there are or how many people live away on the faraway islands. Each one of those islands represents a different parameter set. And the number of people is the likelihood of that parameter set. So, you might have an infinite number of parameters with each one having a different likelihood. That's the case we're considering here. What you can do is find the population of adjacent islands. So if you go back to our calculation here, remember, we can find the prior and we can find the likelihood. So we can find the probability for a single island or a single case. We can find the posterior, but we just can't find, that infinite case. So what we're going to do is take a random walk. And that's what this Markov chain Monte Carlo analysis does. It's doing a random walk along these islands. You randomly choose an adjacent island, I. You find the population of that, which is the likelihood times the prior. And you move if that population is greater than the current island's population. So you move to that next parameter set. And you stay if population is less, and you choose a random number and it's greater than the population of the adjacent island divided by your current population. So again, these details don't really matter, but I want to give you a sense of how simple this is. Because if you do this thousands and thousands of times, you're actually going to yield a number of visits that's proportional to the population of each island. It's just a really cool concept. So this is a way to get a sense of that posterior distribution from using these computational tools. So now that we've kind of got a sense of the vocab and hopefully an intuitive sense of how we got there, we're going to use Bayesian inference to determine this classic case. You got two normally distributed groups and see if they have different means. Okay, so here's the data. We've got y1 and y2, and you can see the histograms here. It looks like the means are pretty close. This data doesn't have to be normally distributed, by the way. You would just use a different function to describe the shape of the data. In this case, I would say they do kind of both look normally distributed, so I would probably use a normal distribution. And we're going to ask, given this data, is there a highly credible difference between the mean of y1 and the mean of y2? So again, think about the way we're phrasing this. This is exactly what we're going to find when we find the posterior, p of theta given d, is we're going to find those parameter values, mu1 and mu2, given the data. Okay, so this question is perfectly aligned with Bayesian statistics. And another way of phrasing this, or maybe something else added onto this, is asking, is 0 included amongst the most credible values of mu1 minus mu2? So is your difference between the means, is 0 one of the most likely values that you're going to find? So what we're going to do, this is maybe if you got another piece of paper, I'm going to show you that this is a really important step, is mapping out your model. Okay. And here's how we're going to do it. We're actually going to start at the bottom of your paper. We're going to start with your data, y1 and y2. again, that data looked normally distributed to me. So I'm going to say that that data were derived from two normally distributed populations. Okay. And I'm just going to list out the parameters included in those distributions. So each one has a mean and each one has a standard deviation. Okay. Now we define our priors. This is where we kind of get away from, or this is what's really powerful about Bayesian statistics, is you get to define your priors. Say for my mean, I think it's a pretty good assumption that your mean is also that if I took multiple tests, of this, or my prior knowledge is that the mean is also normally distributed. Maybe it's a little broader. Maybe there's a lot of different possibilities for that mean. So that prior distribution has a mean and a standard deviation. I'm going to call that M and S. So again, this is the distribution of prior means that are the most credible. So my most credible mu1 is right at the top here. But it's still possible, maybe in my mind or my initial guess, that the mean could be something much farther away from that. This is just my prior guess. Okay. You can do the same thing for every other parameter. You can give priors for each one. Maybe you can use the same values, M and S. Maybe you have no reason to believe they're coming from different distributions. You can do this, and I think the main point here is that you want to be transparent with this. Whenever you're publishing your paper or discussing how you're doing this experiment, you need to lay out exactly how you did it. And that's easy because you can just show exactly what you used for your priors. For my standard deviation, I can't go below 0, so maybe I'm using some other distribution, in this case, a gamma distribution that just tails off to infinity, but doesn't go below 0. And same with my sigma 1. Just going to go from 0 and it goes to infinity. Okay. Not really important what those are because, again, you can choose those based on your best knowledge of the situation. So that's my model. And what you do next is turn that into code. So this code that you're seeing, I'm going to give you this this whole file, and I commented it out as best I can. Don't worry about looking into it right now, because we're going to move on in just a second. But I just want to maybe impress on you that it's not that complicated. There's really not that many lines of code here, and there's a lot of examples in the resources that I'm going to give you on how to write this. This is in Stan. It's an open source language, so there's tons of documentation on how to write in this language. I've already done quite a few different things with this. It's very flexible. But I will say this is probably the trickiest part of dealing with Bayesian statistics. So you have to run the code. You have to figure out how to code this and make it work. So when you do that, when you plug all this in, and again, I'm giving you the file here that you can refer to, and you'll see exactly how to produce these plots. But I'm showing our data in red, and then 20 very likely parameter sets that are plotted. So these are kind of the 20 most likely theta 1 and sigma 1, or sorry, mu 1 and sigma 1. So most likely means and standard deviations. You see they fit the data pretty well. The really powerful part is that I get back from that random walk distributions, the posterior distributions of each one of my parameter values. So what I'm seeing here is the mean mu 1 and the standard deviation sigma 1 for my Bayesian inference test. And these are the most likely means and standard deviations given the data. This is P theta given D. So these plots are beautiful. I think they're absolutely beautiful because even a confidence interval is just going to give you down here. What you're seeing there is the 95% highest density interval. Those are kind of the 95% most likely means. Confidence interval is going to, that's basically what you're seeing with the confidence interval, just a bar. Here, what you're seeing is a distribution. So you're getting a mode. You're seeing actually the most likely mean value, and you're seeing kind of how that most likely means are shaped. Same with your standard deviation. And of course, you get that for your second distribution as well. You see a different distribution of means, different distribution of standard deviations. So what you can do is for every single one of those priors, remember we tested to get this data, I think there's 50,000 tests that I ran. Every single one of those, you can calculate the difference between mu2 and mu1. And you can ask, is 0 among my most credible values? And look at that, 0 is within your most credible values for mu2 minus mu1. So we can say that there's really no credible difference that we can see between these two populations or between the two means, because 0 is within that 95% highest density interval. You can also look at the effect size. You can do whatever you want. You just get a huge table full of those 50,000 values. For every single prior, you've got the posterior values for every single one of those parameters. Very powerful stuff. So there you go. The conclusion is that yes means the two groups are not credibly different, is how we would say that. Try to stay away from that word significantly because it has so much import in null hypothesis significance testing. So one of the great things about Bayesian statistics too is that you can actually accept a null value because you've got these distributions of your posterior parameter values. You can treat these as you might in the most intuitive way that you can think. So for practical purposes, you can accept a null value if it falls within a region of practical equivalence. And again, so here's an example of this. Say that our null value is that the mean is 101 for my group 1. And say that my region of practical equivalence is 101 plus or minus 2. Now, how did I choose the width of my rope? That's again based on prior knowledge, and it's transparent. You have to say why you chose the width of your rope. I actually just published a paper where we used ropes in our analysis, and we actually used an ROC curve analysis, if you're familiar with that, to determine the width of the rope. So we looked at prior data or preliminary data and said, okay, based on that, we think this is how wide a rope should be. And if the 95% most credible means are within that rope, we can say, for all practical purposes, this mean is this value. We can accept this null hypothesis. You can reject it if that 95% falls completely outside the rope, and maybe it's unclear. Maybe the 95% value straddles the rope, and part of it is inside, part of it is outside. Then you would say, all right, we can't really make a conclusion based on this test. So again, you've got a lot of freedom to work with how you define your test, and because your values are intuitive, I think it's a lot more powerful, the results that you get. So finally, last slide here, I just want to do a quick comparison between the p-value and Bayesian inference. Those are the definitions up at the top there, and you can see, for me, the Bayesian inference, the posterior, the p of theta given d, is much more intuitive. They're presented very differently. P-value is a single value. Bayesian inference, you get distributions for each one of your parameter values. Is it dependent on sample size? Both are. It's much more unclear with a p-value what the effect of that of that population is. Are there normality assumptions? In most cases, classic cases in the p-value, yes. No, Bayesian inference, you just decide what your distributions are, and you're transparent with those decisions. Yep, can null value be accepted? Yes, it can with Bayesian inference. Prior data, yes, you can do with Bayesian inference. Dependent on sampling, no, not with Bayesian inference. Widely employed in academia, not yet. So that's where we are. And here are some great resources. This is what I use to learn all this stuff. That textbook is fantastic. And I'm willing to help if you want to give this code a shot with your own data. So with that, thanks. And we have a little bit of time for questions. Happy to answer these. And again, everything's going to be online, so you can try this out for yourself. Any questions? I know it was a lot. I should have done a poll or something. I want to see how people feel. It's hard with Zoom to see where the audience is, but
Hey, Sean, I have a
yeah.
question about R and computers. Is there a particular computing need in order to be able to do R? Because I've talked with some folks who have like older computers, and then can you speak to that a little bit?
Sure. Yeah. I think it really depends. So the data set that I worked with, I think we had like 1.5 million points of data. And that took me a few days with a relatively fast computer to run all that, because again, you have to run like thousands and thousands of samples for every one of your sets of data. But if you have like 50 parameter values, it takes a few seconds, even with an older computer. It's pretty fast. It's just, again, all you're doing is plugging in all your values into equations. It's just plug and chug for a bunch of values. So it does depend on the number of samples. I'd say it's very reasonable. It's very possible with a typical computer to do this for, thousands, even millions of points.
Great. Well, thank you so much for answering that question. In order to be respectful for everybody's time, I'm going to say if we have time for one more question, and if not, look out for the recording of this talk, which will be available shortly. Because you registered today, you will automatically receive an email from me. And we thank you so much for a great presentation, Dr. Koebley. We learned a lot about Bayesian statistics, and I look forward to hearing about this more.
All right. Yeah, I was just looking at the chat and I didn't see any questions, I guess. But yeah, I'm happy to answer those offline. You've got my email. And yeah, thanks. Hope this convinced some of you to give it a try.
Thank you. Bye.